Okay, so let's continue with this. So the idea of pointer is that you will have some sort of variable that will allow you to point to some particular address in the memory. And I was saying that it's actually, so probably you're too young, but I don't know if you remember, some time ago we had 32-bit systems, and then in those systems the pointer variable was only 4 bytes. This means 32 bits. That's why it's 64 bits long, because it's pointing to an address of memory that can be 60 bits long. So far it's easy to understand, but there's nothing weird in this. So there's another example here that you have a pointer to a pointer, and there's some guidelines here, and that's basically it. So I will skip these raw pointers and we will jump right into the pointer to classes. But before, I want to show you one example. Oh, hello Nacho. So I prepare here one example. So where's this? Yeah, take pointers. So it's not here anymore. Right, and then let's create pointers cpp, and let's do it really easy. So this is probably too big. So we have main function here, and then let's do one variable that has 5. Done. And then let's create a pointer to an integer variable, and then let's call it pointer to full, and then we will store the address of full. So this is like a really stupid example. Again, you should try it on your place. Let's build this pointers, and then let's call it pointers.cp.o. And then one thing I want to show you is that I didn't manage to make the debugging tutorial, but one of the ways I learned to use pointers was using debuggers, so I admit, and the funky ones. So this is the Eclipse debugger, so you can install this without installing the whole Eclipse thing. But why this is like easy to learn, because you have like your program here, and then you can inspect the variables, and let's step through this point where all the variables are set. And my recommendation is that you try this debugger or any other debugger you like, and do some sort of like dummy examples with pointers, like the address of this and blah blah blah. And this way, inspecting this 2 lines program, then you will get intuition behind the address and addresses and so on. Also, so here you have full, and then you can, on expressions, you can say, okay, tell me what is in full, and you can also say, okay, tell me the address of full, for example, and this is the value. And for example, if you print the pointer, that is pointer to full, you will get the same value, because inside this variable you are storing actually the address to this this memory address. And also you can, for example, do full and then view in memory. You can open this memory thing, and then, for example, you can say show me integers, and the last thing I will do is reformat. It's a lot, but don't worry, it's just, and this way now you're seeing all your memory. And if you see, so the full variable is on all this blah 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 and 518. So if we find this address of memory here, you will see this 5 here basically. So anyway, so this is something I wanted to show you. If there are like a lot of interest from you guys, you can let me know on the Discord channel, and I will create a more step-by-step tutorial on this. Okay, so using pointers on the real world. So this is where our lesson starts. So pointers can point to objects of any type on C++. So on this case, for example, you have a vector, and then you want to do you want to point to this vector. So if you're doing this, it's basically there's something else that is wrong, so you don't need to do this. There's no reason why you should be pointing to vectors. That's another story. And then let's say you have a type that is called myClass, and then you can create an object pointer, here's a star, to this particular object, and then you point to this, getting the address. Yes, so no matter how big is this object pointer will be always 64 bits. This means for 8 bytes, sorry. So this will only store where it is on the memory. You can also, from the pointer, you can access what is in the memory. So the way you know how to do is you create one object and then you call it with the dot operator the function. But what happens if you have a pointer to this object, to this class? Then how to call this function through the pointer is using the reference operator. So you have the dash and then the angular bracket. So this is like the arrow, and then that's how you call this function. So the syntax is slightly different, but on the behind the scenes it's the same idea. So this is nothing funky to worry about. Of course, so this is basically what's going on. So when you do this operation, what is happening behind the scenes is that you're dereferencing the pointer, the object here, and when you do this, you basically get the object. So when you dereference a pointer, then you get what you're pointing to, and this is when you start thinking like this, you will get into this all sort of trouble. So take it easily, and then you just call the function normally. So this is basically syntactic sugar for this call. And then pointers are just like references, but have additional useful properties. So they can be reassigned to each other, so to different pointer variables. This can point to nothing, so you cannot have a reference to nothing. You can store pointers on any sort of list on C++, and you can use pointers for polymorphism, right? So blue text object is pointer, last slide. So blue text object is object pointer. Yes. You're right. So this is this should be pointer. So from the example, this is object underscore pointer. And yes, you're right. And thanks, Yash. Good catch. So with pointers, you can do polymorphism. So we saw some sort of polymorphism last lecture, I believe. So you can have a derived class that this can be an image, for example, that is derived from a geometry 2D. And then with the pointer to a geometry, you can actually point to an image. So you can have a pointer to the base class and point to any derived class from this particular base class. Of course, you cannot point to other classes, so there must be some relationship between the classes, but this is something you could do. And why you want to do this is because you want your programs to be polymorphic, and maybe you want to work on pointers of geometry 2D types to do some sort of operation, and you don't want to worry about that if this is an image or any other type of variable. So as an example, for implementing the strategy pattern, you would store a pointer to the strategy interface and initialize it with null pointer and check if this is set before calling any of the methods. So we saw a strategy pattern last time. So you can store a pointer to the strategy and then you just work with the strategy without knowing which strategy you're picking. And then the only thing you need to worry is that you should check for null pointer before using this pattern. The example is here because you need to do it for homework number 8, so make sure you go through it. Here's an example of a strategy pattern sort of thing. So let's go quickly through it. So you have an abstract shape. So you have a delete function, and this is virtual. So anyone who inherits from this must implement this function. And then we have a square and a triangle. Both are public shapes. So they both inherit from this, and because this is deleted, then you need to implement the print function with an override keyword. So you're just basically printing the name of the class. We actually saw how to do this much cooler with the CRPT pattern. Well, what I want to do right now, I want to have a vector of abstract shapes. So that's one of the reasons of why you want polymorphism, because you want a vector of shapes, and you don't want to worry about like if this is a triangle, a square, a circle, whatever. And in this case, we want to use pointers, so we can hold pointers to abstract shapes, right? And then this is like we just initialize the data here, and the most important and most polymorphic, let's say, part is this, where you have a loop, and then you just call the shape. So for each member on this vector, you just call the print function, and you don't know if this is a triangle or a circle beforehand. So this shape will be polymorphic, and this is something that will be solved at runtime. Also the classes, so each class in C++ has this pointer. So this is a keyword of the language. So every object of a class or a struct that is the same holds a pointer to itself for many reasons, but you always have this pointer even if you don't use it. So this pointer is called this, and allow objects to return reference to themselves. So for example, let's say you're implementing some class and then you want to return a reference to yourself, then that's how you do it. Create copies of themselves, and explicitly show, this is sometimes for readability, that a member belongs to the current object. So this is on, you have a class function, and then you say, okay, you do some operation with the x, and then there's some other x flying around. If you do, every time you do x, you're actually doing this x behind the scenes, but sometimes you want to express it to show the reader that you are talking about this x, like the x that belongs to this particular object. And also if you want, for example, you have this x variable and then you want to set x, so you write a set method, then maybe you want to use the same name on the argument of the setter, so you can have an x there, but then when you do x, you will have like x equals to x, so this will not compile, and then that's why you do this x equals to x, that is the other one. So something like this you can also do. So this is funny. So pointer is a variable, and all the rules for variables, lifetime, const, whatever, holds true for pointers. So there's just another type of variable. Let me check how much data we have. Yeah, good. So pointers can point to a const variable. This means that the variable that we are pointing is const, and then the type of the pointer should be const. So I'm missing the variable actually here. So this is not a const pointer. So the pointer variable is not constant, but it's pointing to a const type. This is a mess. So there is a bar here, there is declared somewhere here, that this is const. And if I want to point to this, whenever you do const, the const becomes part of the type of the variable. So if you want to point to this variable, then you need to const my type. So you need to create a pointer to a const my type. Yeah, that's the example. The pointers itself are variables, so this can also be const. And how you do it, so believe me, this is funky. So you have a pointer to my type, and this pointer is const. And now this becomes part of the pointer. So, and this is the name of the pointer, so var const pointer. And then this, for example, you cannot do. No, yes, this you can do because a is any variable. What you cannot do is to change the value of the pointer. So this pointer is now const, so the address that is storing cannot be changed. And then pointers can do both at the same time. So you can have a constant pointer to a constant type sort of thing. So just don't get really frustrated. Ideally, you should spend 5 minutes with these slides at your home and try to make sense out of the 4 sentences. And if you have doubts, let me know. But this is basically, it's like a tongue twister. So that's it, nothing else. Okay, so that was the introduction. Again, if I need to be really honest, pointers took me a while to understand back in some years ago. And I guess I finally understood it when I was working with low-level hardware. So I don't even know how people who never program like microcontrollers manage to understand this, because you're always doing these abstractions. So you draw the memory, but you have no idea what is this. So in my case, it was easier to understand when I really knew what was the hardware I was using. But maybe, so my expectation is that you don't really need to know much about this. So if you more or less understand the memory model and what is an address and whatever, the only challenge here is to get through the tongue twister. So pointer to pointer, const to pointer, point to const. So all this weird stuff. It's basically not really complex, but it's like a lot of information concatenated each other. So that's probably my advice. So, but yeah, let's go for stack and heap, because this is the moment where you should be asking yourself why in the world you want to use pointers. So let's quickly discuss about stack and heap. So whenever you're working with a program, and this actually only holds true for operating systems, so programs running on an operating system like Linux, Windows, macOS, you name it. So this is not true if you're using like a low-level microcontroller. But for now, let's pretend that we are using Linux. So you have 2 types of memories. So actually you have one memory RAM, but the way you manage this memory, so you have like one chip, it will be separated into 2. One is called the stack memory, and the other one will be called the heap memory. So the stack memory, you should think is like a stack of variables that you put every time you need a new one. You should just put new variables, and new variables, and new variables. And when you need this variable, you just pop it from the stack. So it's a fast access memory type of thing. And the heap memory is, you should think it like as a bag of variables. So the heap memory can be as big as your memory on your operating system, and it's a bag of variables that are spread everywhere. So you have the bag here, and then you have a lot of variables inside the bag, but you have no idea where is each one. So you actually, if you want to use this bag full of coins, you somehow need to manage this memory. And believe me, this is the key concepts behind all memory management in C++. And it's important, so for me it's more important that you get this idea, that how to work with a pointer to a constant pointer that is there referencing and blah blah blah. So that's the technique, that's how you do it, that's how you will suffer and bleed to do it. So let's discuss a bit about the stack memory. So this is static memory. So I guess you know at this point what is the meaning of static. So it's something that will happen at compile time. So this memory will be allocated at compile time. So you need, I mean, not everything in the memory will be allocated at compile time, but where you place it on the memory RAM will be, this will happen at compile time. And if you know some assembly, you know that there is some particular section of the binary that reference to this particular memory. This will be available for short-term storage. So this is basically the scope of any function or class, and it's actually small. And this is important. So on a Linux system, this is small. So how you check this? Just open a shell. Let me. You do ulimit and then -a, And then if you see now where it is, stack size. So it's 8,000 kilobytes. So this means this is 8 megabytes. That's all you have. So whenever you create a new program, you start the execution, the kernel will give you, okay, here's 8 bytes for you. Use it wisely because you don't have it more than this. And what is one of the implicances of this? That if you want to store a variable that is more than 8 megabytes, let's pretend you're working with an image or a point cloud, then you cannot use the stack, right? So this is important. It doesn't fit on the stack, so you can't put it there, and you will find errors that will be hard to solve because there will be a conceptual error right there. So keep this on the loop. So memory allocation is fast. So this is a stack. So it's like you just put the variables and you take it out. And the structure is a LIFO. So the last in. So the last in is the first out. So if I put this on the stack, the first one to go out is this one. And then, yeah, this push pop, you don't worry. Here's an example. I will not go through it, but basically I will do it. So when you start the main program, so this will be the stack for this scope. So the curly braces will identify this stack frame, and then you say, okay, please create an integer variable, and then you just push it to the stack, and then you put it here. Then you say, please create a pointer to an integer variable, and just initialize it with nothing, so new pointer, and then you put it to the stack. And then you go into new scope. This means that the stack frame will, so whenever you end this scope, the lifetime of these variables will end. So you will need to take it out from the stack. So you create a C-style array here. So you have 2 allocations here, and then you change the value. Here it changes, and here it also changes. And then this pointer you want to point to this array. So you just point to these 2 is this address. So it's actually, this should be an hexadecimal address, right? But then when you reach this point, you just pop all the elements you just pushed, because it's the end of the lifetime for this scope. So you take this out from the stack. So that's how more or less this works. And every time you create a variable, so you're working on a program and you have the function, and you say, okay, floating point b, this variable will go to the stack, right? Keep this in mind. And then the heap memory, it's something that we call dynamic memory. So this will be also dynamic, means it's something that happens at runtime, and this will be available for a long time. So it doesn't, so the C++, there is no such thing. So the kernel, the Linux kernel, will not remove these variables like we did here with the stack when you reach the end of the scope. So whenever you allocate memory on the stack, will be there until your program dies. And then you can do raw modifications with new and delete. So how to work with this memory, you will need to use these 2 operators. So allocation is slower than the stack allocations, because this is not more a stack. So when you actually do new, this is a call to the operating system, and then the operating system needs to go to the memory RAM and look for where it can put these coins you want to allocate on the memory. So this is a really good rule of thumb. So whenever you're doing allocations, keep in mind that this is costly. So this is expensive. So if your program do new every time, it will be slow. But not because it's doing calculations, it's because the operating system will be busy trying to allocate memory for you. So new and delete is something that you don't want to do like a lot. So the users control the memory allocation. So that's the idea behind the heap memory. Now you have a huge memory. So in my case, I think I have 4 or 8 gigabytes. I think I have only 4 gigabytes. So I have a lot of memory. It's much more than 8 megabytes. But now I am responsible for this, for managing this memory. For this, the language gives me 2 operators. That is new and delete. That is basically malloc and the other one on C. So you will use news to allocate that data, And here it's something really, really important. That is, this is a pointer to integer, and this is a variable. So this pointer variable will be on the stack. So keep this in mind. But it will have an address to the heap memory. All these addresses, so at the end of the day, they are all on the same memory chip. So, but the operating system will not allow you to access any kind of memory there. And then with this pointer, you say, okay, new integer, new return a pointer. So this means an address to a memory in the heap. So the pointer itself is on the stack, but the address that is on the pointer, it's pointing to a memory, to a heap memory address. And then this will also work for arrays. So let's say you want to allocate an array on the memory because you want more data. You do the same, but you just use the angular brackets and then you specify how much memory you want. So how much floating points in this case you want there. So keep in mind that you might want to do this for your homeworks. New returns an address of the variable in the heap, and then we will see how to use smart pointers. The problem with this is you are in charge of allocating the memory. And then once you allocate memory, it's like you tell the operating system, go and reserve some of the coins on the back for me because I want to use it. And then the kernel will go there and say, okay, I have these coins for you. But then those coins will be reserved for you until you say, you know what, I don't want this anymore. That's enough. So I already use this memory, just free it. So delete is the equivalent to the free operation on C, and this will free the memory in terms of that any other program can now use this address of memory. So the memory is not freed automatically. So C++ does not have a garbage collection. So Java, for example, does it. So if you locate memory, at some point the Java kernel will go and do it for you, but you never know when this is happening. And the user must remember to free the memory. So this is really important. So let's go to the example again. And now we have this pointer to integer, and then we allocate one integer on the heap. And then after we use this memory with this integer, we need to free this memory. So we need to call the delete operator. And this inter pointer, so inside here there's an hexadecimal address. When we delete this address, we're not deleting like there is like now you lost your memory. You're just saying now you can use this for any other purpose. So this address, I'm fine with it. You can use it for any other thing. The same holds true for arrays. Again, we will see how to deal with this with smart pointers. And then here's a small example on the heap memory. Just try it. Okay, so brace yourself, the memory issues are coming. So far we saw stack memory and heap memory. So with the stack we don't need to actually care about the memory, so we just put objects there, and you have been doing this without even knowing since day 0 on our lectures, and then that's it, it's safe. But then you say, wait, what happens if I want to use data that is more than 8 megabytes, for example? Then you will need to use the heap memory. And you start reading and you say, okay, but wait, in order to use the heap memory, I need to manage the memory myself because the C++ does not do it for me. Then that's why you want to use new and delete operators, and that's why you want to use pointers. Sometimes there's a lot of confusion, and believe me, if you can distinguish this fact, you will know more than 90% of the programmers I know of C++. So when C started many years ago, the way of passing objects between functions was pointers. And this is no matter heap or stack. Why is this? Because C didn't have references like C++. So if you want to, you have a function foo, and you want to pass an object or actually in C you don't have objects, but you want to pass a variable to this function. You need to pass, and you don't want to copy this variable, then you need to give the pointer to this variable. You need to pass a pointer, because you need to say, okay, the reference is here on this particular address of memory. And this for me like made a lot of provoked a lot of confusion on people, because nowadays if you start programming in C++ with references, at some point you will say, why you need pointers? And people just start using pointers just because. And in your case, my friend, the only reason why you will want to use pointers is not because it's fast or you want to do low-level stuff, whatever. It's because you need more data, and the only way of putting the data on the heap memory is through pointers. So that's the key concepts behind this heap memory and the pointers. You should never use pointers to variables that are on the stack, because it makes no sense at all if you can reference this variable. If you have an integer variable and you want to pass the reference to this variable to a function, just pass the reference. You need to create a pointer to this variable and then send the pointer. This is crazy. And before we dive into the issues, let's go through a quick example. So this example is on the slides.zip on the campus. So let me go here and then take danger, I don't know. And okay, I am doing it faster. So let's see for the issues and then we see the example. Is there any question at this point? Okay, so let's go through the memory issues. So first one, the first victim of managing memory by programmers. So people who program is people like me, it's like dumb people. So you will do mistakes. So the first thing that could happen is the memory leak. So this can happen when working with a heap, and if you're not careful. So the idea is that a memory leak is a memory that was allocated on the heap, and the access to this memory was lost. So we have a program, and then we have 2 pointers to any type of object, and then we do new and new, right? So whenever we do new, the operating system will go to the heap and allocate memory for us. And then for some example, we say, okay, now the second pointer, you know what? For some reason, I want to point to the address of the pointer 1. So for some reason, I want the 2 pointers pointing to the same memory. But the problem here is that I didn't free this memory. This means that the operating system reserved this memory for me, allocated for me, and that memory is still there, and no one can use it. So other programs running on the operating system cannot go and use this memory because I am using it. But the thing is, I lost the reference. So which is the reference? So I lost the number, the hexadecimal number, and I cannot access it anymore. And this is the most common mistake ever. So memory leaks is the language of Windows, for example. That's why you reboot your machine every now and then, because there are memory leaks everywhere, and at some point your computer stops working and just reboot it. That's Windows style. And this particular memory was leaked. So you will not be able to access until you kill this program or the program terminates. If you're talking of the operating system, it's until the operating system is rebooted. So here's an example, but let's see it here. So the example is on the slide, so make sure you go and check it out. So these are like all these banners and rules, just utility functions. The important thing is the main function. So we have how much gigabytes we want to consume. So we ask the user for this, and then we print some information, and here we will do the allocation. So we will have data member here, not data member, pointer to double that is called data, and then we will have this size variable. It's basically 1 GB of data, so here's the math, and then we will enter a for loop depending on how much gigabytes we want to consume, and then we will allocate memory. So on each iteration, we tell the operating system allocate this amount of memory. In this case will be 1 GB per allocation. And then this fill is not we're not doing anything, we're just filling this memory with one number, 1.23, because otherwise the compiler will optimize it and you will not see the behavior, the expected behavior of the program. And then you print to the standard output, and then that's it, right? And because you attended to the lecture, you say, okay, now I need to delete this array, right? And then let's see what's happened with this. So let's compile this, memory leak, and then by the way, I will not do it like I do on the lectures on the lecture hall, but usually I try to consume all my memory RAM with this program, and the computer just crashes. So my recommendation is you should try it on your place and try to put as much gigabytes as you can until your computer just crashes. So believe me, it's fun, but if I do it, then we need to do the stream again. It will be a mess. So let's keep it simple for now. So hello hacker, how many gigabytes of memory you want to consume? So I have 8 gigabytes, so 2 will be good, I guess. And then, okay, all right, 2 gigabytes will be consumed. So 1 gigabyte has been allocated, 2 gigabytes has been allocated. And then now it's waiting for my input. So if you actually see on htop, if you see the memory leak here, so I am now using with this stupid program 26% of my memory. And actually, so there's this ugly command, so don't worry, memory leak. Oops, didn't work. So is this map? Let me see if I can. What is the name of this? The name is bad, so let me change the name because this I don't like. So this is memory leak. Oops. So we do it again. I did a mess, sorry. Okay, and then good. And then pmap. Okay, 2 gigabytes. And then if you see this example, so this will give me, so with some black magic will give me how much gigabytes I am consuming, right? And then let's see the program again. So the memory, so here is the delete operation. So after this delete, we should have 0 gigabytes consumed. So again, 2 gigabytes, and then press enter to continue. And if we inspect after the delete, we are still using 1 gigabyte, right? So this is what is called a memory leak. So after you even think that you finish, and if you continue, just abort, right? Freeing your memory, you're not. So what is the problem here is that every time you enter this loop, you're allocating 1 gigabyte, and here you're only deleting, also known as freeing, 1 gigabyte. So the problem is that this delete should be here and not there. And why is this? Because, or you put here, like you do a for loop here and then just call delete 5 times, but this is stupid. You will never do a program like this, but my recommendation is try to play with this program at your place and actually try to use htop, and you will see that when you do the allocation, try to do 8 gigabytes, you will see that the CPU usage is 100%. So it's costly to allocate memory. So, and here I have one other example, just try it. But with this thing, so there is something very important I also don't want to forget to mention, is that you might say, Nacho, wait a moment. You're telling me that even if I leak memory, when the program terminates, then that memory will be free. And you say, yeah, that's true. But there is one problem with this. You're not thinking big. Because for robots, for example, the program never ends. So if you're running a robotics application, the main program will start when you boot the robot, and then it will never stop. So if you leak memory during your program execution, you're losing memory that cannot be used by any other programs in the robot or even the application, like any other threads. That's the important idea of memory leaks. So you have a memory leak on your Chrome browser. You open the browser and then you start surfing to the web. Until you don't close the browser, the memory leaks will be there. This means that you're consuming more memory for no reason. So it's important to understand that on this example, after you return 0 here, all the memory will be free. So even if you don't delete anything. So for stupid small examples, you don't care about memory allocation, because after 1 millisecond, the memory will be free because the program will end. The problem is when you are doing long time running processes. And believe me, once we spent, because it was a full team dedicating on hunting memory leaks, because this is how much? 50 line programs. It's easy. But when you get to 50,000 lines program with all these sort of things, it's really hard to detect these memory leaks. So believe me, it's really bad idea to do this sort of memory management by hand. So memory leaks was one of my biggest headaches across my programming time. I hope that you never suffer this, and it's the most common mistake, I would say. Of course, there are tools to help you with this. So if you run this program and then you use this sanitized address for the compiler flag, there is something that is called valgrind that will help you to detect these errors. So this is the example we just saw, and that's it. So be careful with memory leaks. So it's 12. We should stop now, but I really want to get this done. So let's do a 5 minutes break. Okay, so let's finish with memory issues. So there is another issue that is also really common, that is called the dangling pointer. So you have 2 pointers, and for some reason you are pointing to the same address on the heap, of course, and one of them will delete this address. So after we call this line 3, you delete this pointer, then you free this memory. And then pointer 2 is still pointed to the same memory address. So I have no idea who is. The video is going to be from 30 more minutes. Anyway, so once you delete this memory, then this is free, and then you cannot use pointer 2 anymore because the behavior is undefined. So you're pointer to a memory address that you don't own. So you have no idea what could happen with this. So this is basically when you point to a free memory, and this is actually like the opposite of a memory leak. And the referencing a dangling pointer will cause undefined behavior. So you don't know what to expect, so no one can tell you how your program will behave when this happens. So here's an example of the dangling pointer. Again, just try it. I will not go through it because it's super easy. And here's like an even worse example when used with functions. Okay, thank you guys. So we had the memory leak so far, and then also the dangling pointer, that is sort of the opposite. I would say that the most dangerous memory leak, again, because your program might run more than 2 seconds. And there is also something called RAII. There is resource allocation is initialization. So this is something that C++ people loves to say. Mute your video, down spam. Okay. New object, it's must allocate memory, and when you remove the object, you must free memory. So you say, okay, I know classes, I know how to write constructor and destructor, all this new and delete thing that Nacho tell me that is complicated, I will do it because I'm a smart guy. So it's easy. Whenever you have a class, so let's say you're holding a pointer to another class, that this, for some reason, this class must lie on the heap memory because it's a huge object. And then whenever you call the constructor of my class, then you will call the new operator and you say, no need to do it manually. And whenever you call the destructor, you will delete this memory. This means you will free this memory for someone else. And then you will just point to null pointer to clean up a little bit. So we could stop the lecture now because you say, that's it. So we already solved this new and delete thing. We just wrap it into a class and then we're ready to go. And I say, yes, but what happens if you want to copy this object, for example? And then let's, oops, spoiler alert. Let's go through this example. So first we have this class that is the same that from previous slides, so this didn't change. And then for some reason, first let's create an object of the class A, and what will happen is that I will do my best to write here. So let's try this pen. So actually, so you will call the constructor, right, of my class. So whenever you create an object of my class, then you will call this constructor, boom, you're allocating memory, right? And then, because you didn't define a copy constructor, so when you copy this object through its copy constructor, remember the compiler will generate this for you. So even if you don't define this, it will be there. So when you do this sort of, with this syntax, you're creating an object B that will be a copy of A. What is the meaning of this? You will basically copy all the data from A to B. And what is the data? In this case, we only have one data member. And copying this data, it's a pointer. So this is a variable pointer, variable. So inside data underscore, it's only one memory address. So when you copy this, you will have the same memory address than A here. So far, now there is no problem. But what happened when you reach this point? Because when you thought that you were smart, you did let's clean this, it's too much colors. So what happens when you reach the end of the scope of the program? You thought you were smart, and then you define this destructor. So you say, okay, I have A, I will destroy A, then I will call the destructor, and then I free this memory. It's good. But then you have B, and B was a shallow copy of A, so it was pointing to the same memory address. So you will try to free again the same memory address. So this is a problem, and you will get an error that is called double free or corruption. The good news about this is that this will happen on this example. This will happen when you end the program. So you will see all the expected behavior, and then at the end, instead of finishing smoothly, it will just crash at the end of the program. And why is this? Because you're doing a shallow copy. So because you didn't define a copy constructor, you're just copying the pointer data, that is the memory address, and that's it. What you should do instead is to do a deep copy, that this will basically means copy all the data that is pointing from this object. And then how to do this? So there's basically, if you do resource allocation is memory blah blah blah, then you will basically end up on this thing that is a dangling pointer, because you're pointing to a memory that is already free. And then how to fix this is using the rule of all or nothing. So remember, if you define a custom constructor, then you need to define the 6 special functions. So the copy assignment operator, the copy constructor, the move assignment operator, the move constructor, the destructor, and the constructor. So there are 6 special functions. So, and when you define the copy constructor, then you will need to copy the data. So on this, you will just need to get the data that is on some other class and allocate new memory for the copy of A into B. And that's how you solve this issue. But there's a much better life since C++ 11. So C++, after 30 years almost, they were struggling with this, but now there's something that is called smart pointers that will somehow do this for you. So this is the last topic of the lecture of today. So you already know or knew about raw pointers. Then we motivated the fact that we want to allocate more memory on the heap, and that's why we need to manage this memory with new and delete. And then we realized that there are all sorts of errors when we do this by hand. And what is the meaning of this is that we will struggle, we will have memory leaks, dangling pointers, and you will spend more time debugging than actually implementing ideas. So people already encountered this fact, this error, and trying to make it better. So that's the idea behind smart pointers with C++, with the core language, with core techniques and really simple ideas. We can improve this and make the language safer and easy to use. This has been there since 2011 on the standard, but there is something called boost share pointers and unique pointers. So the boost smart pointers are there since 2005, I guess. So it has been 15 years since the smart pointer idea. What is the meaning of this? I don't want to see handcrafted memory allocations on your code, because you're actually writing 40 years old code if you do this. This still happens. You go to open source libraries, cutting edge bleach research paper, people still do it. And it's something that drives me crazy, because there is no real good reason to do it. It's just because you don't know how to use smart pointers. And the problem with smart pointers is the name makes this look smart, and it's just like a wrapper to a pointer. So if it's the same idea of a vector. So, but instead, so a vector, by the way, this is important. std vector will allocate always memory on the heap. So keep this in mind. So it's just a little advice for your homeworks. So a vector, so instead, if we call, so a vector is basically a smart array, but they didn't call it a smart array. Otherwise, so I think the name is not the best one. So instead of smart pointer, I would put like manage pointer or something like this, because it's not really smart, right? It's the same as a vector. A vector underneath, if you open the std vector implementation, is an array, but with some other functionality. And we didn't call it that smart vector or smart array. So anyway, let's go deeply into this. So raw pointers are really hard to load. Its declaration doesn't indicate where it points to a single object of an array. So you can point to an array or a variable with the same pointer. Its declaration reveals nothing about whether you should destroy when it points, or about the ownership of the pointer. So whenever you see the pointer in the program, you know if you need to free the memory. So there's no real information about memory management on this. And then if you determine that you should destroy what the pointer points to, there's no way to tell how. So you should you use delete, or is there a different destruction mechanism, like a dedicated destruction function to the pointer, whatever. So this is really hard to define. And if you manage to find out that delete is the way to go, reason one means it may not be possible to know where to use the single object delete or the array form delete. So depending on this is an array or whatever, you don't know which delete to call. You say, Nacho, this you can see it on the implementation. Yes and no. Remember, if you have really big programs, this is not straightforward to find. And there is typically no way to tell if the pointer dangles. This means that points to memory that no longer hold the object, so we saw the dangling pointers. And then dangling pointers arise when objects are destroyed while pointers still point to them, right? So we say we are C++ programmer, we can do much better than this. Smart pointers. So smart pointers grab a raw pointer, so there is a raw pointer underneath, of course, into a class and manage its lifetime with RAII. So resource acquisition is initialization. Smart pointers are all about ownership, so you always need to think on the ownership level, and always use smart pointer when the pointer should own heap memory. Again, if it's a small object, just throw it to the stack. If this variable should not be alive during the runtime of your program, just throw it to the stack. It's fine. You should use the stack. There's nothing bad with the stack. But if you need this variable to be shared across multiple threads across your program, then you probably need to throw it on the heap, because it will be there until you free it. And only use them with heap memory, right? Never point to a stack memory. There's no real good reason. I don't want to find you in your programs pointers to stack in the memory. I will just completely ignore your homework. Just don't do it. And this still use raw pointers for non-owned pointers and simple address storing. So I have no idea what I want to put there. And to use memory, just include the memory header file that is part of the C++ standard library. So C++ introduced 4 types of pointers. We are only focusing on 2, so unique pointers and shared pointers. The rest just ignore them. And this is the only pointers you should be using for now. And then the smart pointers will manage memory for you. So smart pointers, apart from memory location, behave exactly as raw pointers. So that's why it's smart pointers. It's still pointers. So you can use the dereference operator to get what you're pointing to. You can use the arrow operator to access any methods. The smart pointers are also polymorphic, so you can do the abstract shape example with the vectors as well. And there's additional functionality. So this is the same as the vector. So you will throw a pointer inside the smart pointer class, and then you will provide additional functionality. So there is one get method that will return the raw pointer that the smart pointer is managing. So the smart pointer is a class. This is a new type. It's not a pointer itself. Of course, because the C++ language allows you, when you do this, it's not because it's a pointer, it's because there is an overload for the dereference operator inside the smart pointer class. The same holds true. There is an overload for the arrow operator inside the smart pointer class. And if for some reason you really want the raw pointer, so the 8 bytes of information with the hexadecimal address, then you can call .get that will give you the address of this pointer. Not the address, the pointer. And then you can also do reset, that this is basically doing like equals to null pointer. So this will stop using currently managed pointer and freeing its memory if needed. And then sets pointer to raw pointer. So these are like methods from the smart pointer class. Again, I wanted to change this vehicle example for real stuff, but sorry, that's what you get. So we have unique pointers and smart pointers. So in this example, we will create an unique pointer here to a vehicle type. And this will be called vehicle1, and then we will call this utility function that is called make unique. sorry, make unique, and then we will say this is a bus because pointers are polymorphic, so we can point to a vehicle and create a bus. And that's basically it. So all this stuff is, so when you call make unique, inside make unique, there's a new memory allocation. So there's a new bus, whatever. So this is happening. You are allocating memory on the heap. It's not something that you stop doing it, but the thing is all this functionality is now managed inside the make unique class. So this make unique pointer, sorry, unique pointer class. And there is another example here. Instead of bus, we will use car. It's the same. And now you can have fun, a lot of fun, as we had with raw pointers. So we can do vehicle one, and then call the raw operator, and call print, and whatsoever. So that's basically the syntax. The first type of pointers. So there are two pointers, smart pointers, unique pointer and shared pointer. So unique pointers are unique, you guess. This means that we can move stuff but not copy. What is the idea behind unique is that whenever you have a unique pointer, you only can point to one memory location. So you own this memory location, and there's only one pointer who can access this memory location. Unless at some point in the program, and that's why we saw move semantics two lectures ago, you say, you know what, this unique pointer I own, I don't want it anymore. And then you move it to somewhere else. That basically you're not moving anything. Remember that std move will take ownership of the object. So vehicle one is a unique pointer. For some reason you don't want to use it anymore, but you cannot copy, so you cannot do vehicle one. So if we had this, if you try to do this, like vehicle 2 equals to vehicle 1, remember these were pointers, unique pointers, then you will get a compilation error because you cannot copy the content of vehicle 1 because it is unique. But you can move. This means you can take ownership. This means vehicle 1 will not be used anymore. I will take ownership of this object with std move. And then this is an example of the others of the pointers of before the move. Again, you can try it. There is source code for these examples. Just try it. So before the move, like both pointers had some address, so 70 and C0. And after the move, now vehicle 2 is uniquely pointing. So where is the highlighter? To this memory address, and then vehicle 1 is 0. So vehicle 1 was free because now vehicle 2 took ownership of this pointer. And actually, let's check. Yeah, so vehicle 2. So first it was, let's compare the last two exa, and then this is 70, and now vehicle 2 points to vehicle 1 because here we took ownership of vehicle 1 of this unique pointer. And then, wait a moment, you didn't use new and delete. No, that's the idea that unique pointers are smart, right? So you do this, but inside the unique pointer class. So you don't worry about new and delete. So a really good rule of thumb is that if your program has the new keyword, so if you grep through the program and there is something saying new or delete, there is an error. There is a memory leak for sure. Maybe not, so they're like really stable libraries out there that if you do this properly, then there's no real error. The problem is that if you have the chance to make the error and no one will stop you, then it's very likely that you will do it. But if you use unique pointers, then the compiler will stop you whenever you want to do something stupid. So why don't you use unique pointers or smart pointers, whatever. So again, if you have new or delete on your program, then it's most likely an error. So the constructor of unique pointer takes ownership of a provided raw pointer. There's no runtime overhead. So if you benchmark raw pointers and unique pointers, the speed is the same. This means there is no real good reason of not using unique pointer. And this is the syntax. And there's another thing here. So before C++ 14, you had to do new here, but just forget about this. Just let's do this. Let's ban this. It's ugly and all. And now you just do make unique, and then you specify the type as a template argument, and then you specify the parameters of the constructor here. What makes this unique? That has no copy constructor. This means that you cannot copy, compiler error, but can be moved. So there is a move constructor and move assignment operator. And there's a guarantee by the compiler that the memory is always owned by one unique single pointer. And then, yeah. The idea of unique pointer is that this should be your default pointer. So if you are lost and then you know which pointer to pick from shared pointer and unique pointer, just use this one, because at least it's the same. There's no overhead of using raw pointers, and then it's much better because you don't have the memory leaks and dangling pointers whatsoever. And then lastly, there's this thing called shared pointer that is basically another type of smart pointer that will be shared across instances on your program. So an object can be accessed through its shared pointers, and its lifetime will be managed by those pointers through the shared ownership. This means many parts of the program can somehow participate on this ownership. So one function, one object of a class can somehow participates on the ownership of this shared pointer. So no specific shared pointer owns this object, so it's not like a unique pointer. So you don't own an object through a shared pointer, you just somehow share this ownership. And when the last one standing shared pointer gets deleted, then the shared pointer will destroy the object that is pointing to. The construction is the same as unique pointer. This can be copied because it's a shared reference, so you can copy this. The stores a usage counter and a raw pointer. So inside the class, so if you go to implementation, you will see a raw pointer and a storage use. So every time you copy this shared pointer, then the counter will increase by 1. And every time you destroy it, then you will decrease by 1. After you are the last one on the list, you need to free the memory. Actually, the shared pointer will do it, and then can be initialized from a unique pointer. So there's here the syntax. Instead of make unique, you will use make share, the same syntax, right? And here's like one simple example so the example is easy, so you can try it on your home. So let's just highlight it. So we have one class, and then you have one destructor and one constructor and one destructor. So we will allocate this on the heap memory through a pointer. So we have a pointer to a pointer, sorry, and then you will make sure, and then you will call my class and the default constructor. So this will allocate memory in the heap. And then the pointer, this shared pointer, has this use count method. So you can actually see how many people is accessing. You know what, let's try it. It's better to just see it. Sorry. So shared pointer, and then yeah, why not? Let's try it. Let's do it. My computer is going to die. 8 plus. Good. Let's make this beautiful. And then, yeah, let's go basically here. So let's compile this program and then share pointer example. Yes, let's do it. You need standard C++17. And then we have here a out, and then this is the output, right? So let's go step by step. So here you create a pointer, and just to let you know, so if you're using clandy, you can autocomplete all these functions. So the first here, so cout, like, let's change this and put pointer count. And then let's copy this. Oops. Okay, let's compile this again and run it. So first, when you create, you call make share, you will call this constructor and you say I'm alive. And now you increment the counter of the share pointer by 1. So when you call this use count, you get pointer count equals to 1. Then you enter a new scope here, and then you can copy this pointer. And this means B, that is another pointer, shares. Crazy. Reconnecting successful. I'm back online, right? Yes. Oh, mamma mia. Anyway, so whenever you reach this point, you will call the share pointer destructor and you will say, okay, just be careful. There's another guy who is also pointing to this object. So you just decrement the count and leave it like this. You don't free the memory because someone else is using it. And then when you call this use count, you will see that now it's 1. And when you reach the end of the scope of the program, you will call the share pointer destructor. You see, okay, the count is 1 and I am destructing this pointer. This means that I am the last one standing, so I need to free the memory. So I will go and call a delete operation for this memory address and I will free this memory. But if you see here, there's no new and delete whatsoever on the slide, on the code. So this code is correct and will always work and will never give you any error, memory leak, whatever. Again, try it, debug it, do whatever you want. When to use what? Basically, use smart pointers when the pointer must manage memory. By default, use unique, right? So if you need to start using something, just use unique, and then you, worst case, you change it to share pointer. The syntax is the same, so you just need to rename the unique for share. If multiple objects must share ownership over something, use the share pointer to it. And then think of any freestanding new or delete as a memory leak or a dangling pointer. So if you see new in the code, you say, okay, this is going to be a memory leak. Maybe not. Maybe the programmer who did it properly, but this is not so common. And believe me, even really experienced programmer can do this mistake. So just use smart pointers. Don't use delete, bad guy. Don't use new. Allocate memory with make unique and make share. And only use new in a smart pointer constructor if you cannot use the functions above. Let's say that for some reason the unique pointer or make unique or make share you cannot use it. Actually, you will never. So unless you're not using C++14, you will never see the word new on the code. So you should not use it. So forbidden. And then this is a typical beginner error. So if I didn't convince you about the difference between the stack and the memory, you can do something like this. So first of all, you allocate one variable in the stack, integer, and then you will create a pointer to this variable, and then you take the address of this variable. First error. Why you're creating pointers to memory that is allocated on the stack? So there's no real good reason of doing this. If you want to pass this variable as a reference to a function or an object, just pass the reference. So you don't need to point to this type of variables. And then you say, I'm smart, I know stuff about pointers. So you create a unique pointer to an integer type, and then you can initialize actually this pointer. So if you already had a raw pointer, there's a constructor, unique pointer constructor, that takes as input argument a pointer, and then you use this pointer to A, that is this guy over here, right? And then you try to do the same with a share pointer. And what will happen here? It's a really funky error, right? So you have this boom map chunk, blah, 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 blah. The problem here is that you're creating a smart pointer from a pointer to a stack managed variable. and then the variable will end up being on both but the smart pointer and the stack and gets deleted twice, right? So you're deleting it twice. The share pointer will delete it, and when you reach the end of the scope of the program, you will also delete it. So remember, that's why you see program terminated correctly. You will see this message and then a coredown, right? Why is this? It's because there is a conceptual error, right? That you should not point to memory to stack variables, to variables that are on the stack memory. I'm sorry, I'm tired. And then the last example is that we actually saw this on lecture 7 or 6. So you can create a vector of unique pointers of rectangles. And remember, this is the example of the abstract shapes. And then just place back the rectangle and the square. And then you call make unique. And this is the parameters of the constructor. And then you can do polymorphic stuff like printing, like shape print with the arrow operator. So that's basically it. So as summary. So raw pointers, verboten. I don't want to see this in your code. So we saw a really quick introduction on how to point to classes and how people were doing this before raw pointers. We also saw an introduction, and this is super important to me, that you understand the difference between the stack memory and the heap memory, two types of memory on your system. We also saw that if you think you are smart and then you just manage the heap memory by hand, then you will end up with memory issues. And even when you try to wrap up functionality into classes, you will see errors, memory issues. That is one of the most common issues on C++ programs. And then we saw how to solve all this mess with smart pointers. But actually, you don't need to do anything. They are there for you. You just need to use it. So no new, no delete, no malloc, no free on your programs. Now I don't want to see this, right? And then finishing, there's this like 10 minutes video on smart pointers. If you want to see it, I highly recommend this. And also this guy, Artu Otwire, is really cool guy. And there's like a 1 hour lecture sort of thing on smart pointers that is much deeply. So I really recommend you to watch this video and also to follow CPPCon, that there's a lot of information there. The reference here, I hope I convince you to use smart pointers. I hope that you more or less get some key ideas of what you want to use the stack memory or the heap memory, why the memory leak is a real problem on real applications and whatsoever. Sorry for the mess with OBS on YouTube and whatever. Next lecture is going to be all about templates, metaprogramming, and really fun stuff. Homework 8 is out, and then I need to close the stream because I need to rush and leave. Thank you for your patience, and thank you for staying with me for 1 hour and 40 minutes. I really appreciate it. I hope you enjoyed the lecture, and bye-bye.